Okay, students, in this chapter we're going to begin a topic called Intermolecular Forces, and we're going to abbreviate that IMF. IMF, Intermolecular Forces, with an S for plural. So here we go. Strong attractive forces between two atoms in the same molecule. So notice the expression here, between two atoms in the same molecule. When two atoms in the same molecule are attracted to each other, these strong attractive forces are just called bonds. Right? And that's what we've been talking about when we talked about covalent bonds and so forth. However, there are also weaker attractive forces when we're talking about between two atoms in two different molecules. Such attractive forces are called intermolecular forces, or IMFs, abbreviated IMFs. So intermolecular forces are not within a molecule. We're not going to be talking about any sort of forces that are between two atoms that are in the same molecule. We're specifically talking about forces that are between one molecule, for example, a water molecule, and a neighboring water molecule. So they're obviously not bonded together, but there are some attractive forces. So here again, we're not talking about, here's our water molecule. We're not talking about these attractions. That's a bond. But the attractive force that this hydrogen may have for that oxygen, they're not bonded together, but there's an attractive force there, and that's called an intermolecular force. The term intermolecular, the prefix inter, I-N-T-E-R, means between different, and then molecules, between two different molecules. The same way that an interstate highway is a highway that goes between two different states. So we're going to talk about the four main kinds of intermolecular forces, and they depend upon the kind of substances that are involved. And the first one that we're going to talk about is London Dispersion Forces. So London Dispersion Forces are also called van der Waals attractions or forces. VANDERWAAL'. Van der Waals forces. So London Dispersion Forces, these are usually the weakest kind of intermolecular force, but not always. So we're going to start with these. These are forces that every substance has these between one molecule and another, for example. And these are usually the weakest. IMFs. And there's something very important about the London Dispersion Forces, and that is nonpolar molecules experience only these. So let me abbreviate these. London Dispersion Forces, we'll call them LDFs. LDFs, or London Dispersion Forces, are a type of intermolecular force. Every substance has them. They're usually the weakest type of intermolecular force. And for nonpolar molecules, London Dispersion Forces are the only IMFs that they have. So I'm going to cross out these water molecules because they do not apply here. We'll talk about those here in a moment. Yes, water molecules do have IMFs, but let's deal with a nonpolar molecule for now. Let's take, for example, a diatomic H2 molecule. There's hydrogen gas. That's a molecule. It's covalently bonded right there. That is a bond. And we know that that is a nonpolar molecule. When we have a nonpolar molecule, it means that neither of these atoms is attracting the electron density more toward it than the other. So this is an even distribution of electron density in this molecule. And I'm just going to draw a general sort of an outline or contour. And this is the cloud of electrons. The cloud of the electron density that's around that molecule. And you can see there's some around this atom, there's some around that atom, but the cloud, as they overlap, it generates one big cloud, and that's the overall distribution of electron density. It's a nonpolar molecule, so the electron density is evenly distributed over both of those atoms. So in general, there is no dipole. Remember, a dipole is when we have one end of the molecule that has a partially negative charge and the other end is a partially positive charge. That's not happening right here. Not usually. However, what can happen in nonpolar molecules is that this cloud of electron density, this is a quantum distribution of electron density. And in a quantum distribution of electron density, a little bit more of the wave function of the electrons can be on one side of the molecule at any given moment. And so what can happen is, even though there is no regular, standing, permanent dipole on this molecule, we can get a very small, very temporary distribution of some of this electron density that shifts out that way, so that the whole electron cloud shifts slightly. For example, in this case, to the left. And when it does that, you'll see then that we have a little bit more electron density on this left side compared to the right. And in doing so, we have a very tiny partial negative charge and a very tiny partial positive charge. And this happens very, very quickly. It's only temporary. And in the very next microsecond or less, in the very next nanosecond, this unevenness of distribution goes away as it shifts back to being evenly distributed. So the way that we describe this is we say that it is a temporary dipole. It is not a regular permanent dipole because this is a nonpolar molecule. It's just a temporary dipole that happens on the nanosecond or even femtosecond timescale, and then it goes away. Well, imagine that another neighboring H2 molecule, we're right next door, and it also has its nonpolar even electron distribution. It doesn't have partial charges anywhere because there's no dipole. But when its neighbor molecule does this and creates these tiny temporary dipoles. That partial positive right there can induce or cause or create a slight shift in the electron distribution over here. So the electron density of this cloud will be slightly attracted to that positive, partial positive there. And in doing so, we end up getting a partial negative generating there and a partial positive generating there. As a result, the temporary dipole that has occurred here because of the quantum fluctuations in that electron distribution has caused or induced a small dipole in a neighboring molecule. So we call that an induced dipole. This happens on a very, very, very short time scale. The dipoles that are created are temporary. They're extremely small compared to the dipoles that we would normally see, for example, in a normally polar molecule. These are nonpolar molecules that are doing this, right? So these temporary and induced dipoles can cause a very small intermolecular, between two molecules, attraction. Notice that there's a partial positive over here, a partial negative over here, and they can attract each other. This is what's called a dispersion force, specifically a London Dispersion Force. And this sort of dispersion of the electron cloud can happen in any substance. It can happen in nonpolar molecules, polar molecules, ions, and so forth. But it's for nonpolar molecules especially that this force becomes important, because the nonpolar molecules have no other forces. This is the only intermolecular force that a nonpolar molecule is experiencing. So again, every substance has these sorts of LDFs. They tend to be the weakest, but not always, intermolecular force. And for nonpolar molecules, they're the only force that they have. And so therefore, they're particularly important for nonpolar species. So those are London Dispersion Forces, LDFs. Typically, but not always, typically the weakest of the IMF types. All right, let's move on, and we're going to talk about the next type, which is dipole-dipole interactions. So dipole-dipole interactions, dipole-dipole. And dipole-dipole interactions, they only occur with polar molecules. So a dipole-dipole interaction, or dipole-dipole force, only occurs between two polar molecules. And that's because it's an interaction between the dipole on one polar molecule and the dipole on another polar molecule. So it's between the dipoles of two polar molecules. So here's an example. We've got a polar molecule here, HBr. And it has its neighbor, HBr. We talked about how when we have a nonpolar molecule, there is no regular or permanent dipole, but they can generate very small, very temporary dipoles that then almost immediately go away. Well, now these are polar molecules, and so they do have a permanent dipole. So if I'm just going to show the electron distribution It would be rather more dramatic than this, the difference, but this will be sufficient to illustrate. There is a difference in the electron distribution in this polar molecule. We have a partially positive end, we have a partially negative end, we have a dipole where the electron density is being pulled toward that bromine because bromine is more electronegative than hydrogen. And here we have a neighboring molecule of HBr, which again is polar, so there is a permanent dipole because it is a polar molecule. There's a permanent standing dipole. And you can see right away that there is going to be an attractive force between the partially negative end of this molecule and the partially positive end of this molecule, right? So here's our IMF. And the same way up here we had an IMF. What's the difference between these two? Both of them are intermolecular attractions. This is an IMF that occurs between two nonpolar molecules. This is one that occurs between two polar molecules. Okay, so there's our first two types of intermolecular attractive forces. Can you see why the dipole-dipole interaction, the dipole-dipole force, typically would be expected to be stronger than the London Dispersion Force? It's because the polar molecules have permanent dipoles and the partial charges are large, usually, compared to the tiny partial charges of the temporary and induced dipoles of nonpolar molecules. Well, let's move on. We've got a third type here, and it's called hydrogen bonding. So, hydrogen bonding, first of all, it's a special type of dipole-dipole force. So hydrogen bonding is a special type of dipole-dipole interaction. What makes it special? Well, it occurs between two molecules, and that's true for the others. It occurs between two molecules. But there's a special case here. Within the molecule, there has to be a certain kind of bond within a molecule to make this happen. And we have to have a hydrogen bonded to, and there we do mean bonded to, directly bonded to, a nitrogen, an oxygen, or a fluorine. So within a particular molecule, we have to have a hydrogen directly bonded to either a nitrogen, oxygen, or fluorine. And the classic example of this is the water molecule. So here's our water molecule. It's a bent molecule because of the electron geometry. I'm not going to show the electron pairs up here, but we know that there are lone pairs up here. And I'm going to draw another water molecule over here, a neighboring molecule. So notice, first of all, how this molecule meets this requirement. Within the molecule, within the water molecule, hydrogen must be bonded directly to a nitrogen, oxygen, or fluorine. And there we go. Within the molecule, hydrogen is directly bonded to an oxygen. So water molecules meet this criterion. But the hydrogen bonding that we are talking about here as the IMF is not that bond. And I know this is confusing. This is one of the worst named things in all of chemistry. There has been an effort to change the name of this intermolecular force from hydrogen bonding to hydrogen bridging. Because by calling the intermolecular force the hydrogen bonding force, it makes people think that we're talking about that right there, the way that hydrogen is bonded there. But this is not the hydrogen bond. This is a bond between a hydrogen and an oxygen, but it is not the hydrogen bond that this intermolecular force is talking about. Remember, hydrogen bonds are IMFs, they're intermolecular forces. So they are not within a molecule, they are between two separate molecules. So let me draw the electron cloud, the quantum distribution of electron density here. We have a little bit around each of the hydrogens, and then a lot of it up here, right? Because we have the electronegative oxygen, and we have these lone pairs up there. And over here I can do the same. A little bit of electron density around each of the hydrogens, and then a lot of it around the oxygen. Okay, so there's a distribution of electron density. I think you can see how we have a dipole here. We have partially positive hydrogens and a partially negative oxygen. So partially positive, partially negative, right? Partially positive, and partially negative. Okay, they're polar molecules. They have a standing permanent dipole. So we're going to have a type of dipole-dipole interaction here between these two. And you can probably see that I've got a partial positive hydrogen and a partially negative oxygen. And so there's going to be intermolecular force attractions right there. And there's our IMF. There's the intermolecular force. What do we call that intermolecular force? Well, it is a special kind of dipole-dipole force. And it is a special kind of dipole-dipole force because within each molecule, we have a hydrogen directly bonded to the oxygen. Why does that give us a particularly strong special kind of IMF? And there are a couple of reasons. First of all, the first reason that this IMF is particularly strong is because this bond is particularly polar. Remember, nitrogen, oxygen, and fluorine are very electronegative. And so when they are bonded to a hydrogen, it means that this bond right here is especially polar. And that draws electron density toward the oxygen more than, for example, if this were some other atom. So we have particularly strong polar bonds, polarity to the bonds. That's one factor. The other factor is there can be orbital overlaps between the hydrogen and the oxygen of neighboring atoms that are especially effective because the orbitals are fairly close to each other in size. There is a size disparity, but they are still fairly close to each other, relatively speaking. And so because of those two factors, we get an especially strong intermolecular force here. It's an especially strong dipole-dipole force, and because of its special strength, we give it a special name, and we call this a hydrogen bonding force. So where is the hydrogen bonding intermolecular force? It's this right here. Because remember, hydrogen bonds as intermolecular forces are happening between two separate molecules. Where is a hydrogen bonded? There's a hydrogen bonded, right? Where's the hydrogen bond? It's right here. And you can see how confusing this can be, right? All right. We're going to move on. One more that I'll include here is called the ion-dipole interaction. So ion-dipole force. An ion-dipole force is between the ion of an ionic compound, and the dipole of a polar molecule. So just as the name describes, we've got an ion interacting with a dipole, an ion of an ionic compound that is reacting with the dipole of a polar molecule. So this implies that we are dealing with a mixture. Because we not only have an ionic compound, we also have a polar molecule. Remember, molecule is a covalent species. So the classic example of this is when we take an ionic compound like NaCl. It would work for NaOH, but I prefer to show you NaCl because we're much more familiar with sodium chloride. That's an ionic compound. And we mix it with a polar covalent molecule like water. So I'm going to put some sodium chloride in some water. Now what happens when I do this? Sodium chloride is going to dissociate, right? It's going to form Na plus and Cl minus. The reason that an ionic compound dissolves in water and breaks apart is because by breaking apart, each ion can engage in ion-dipole interactions with the solvent, which is the water. So I'm going to draw the water molecules in here. So sodium has a positive charge, and now a water molecule is going to come up here and associate with this sodium so that the partially negative end of a water molecule is going to be attracted to the positive sodium ion. So for example, so I have the partial negative oxygen that is now associating with the positive sodium ion. And you can now see, of course, that I have the partial positive hydrogen that is now attracted to the negative chloride ion. And when I do that, I get the ion-dipole interaction between the ion of an ionic compound and the dipole of a polar covalent molecule. Okay, so here is the ion-dipole IMF right there. And this helps to explain why compounds are soluble at all. If you had sodium and chlorine, positive and negative ions together, opposite charges attract, right? So you might think that they would like to associate with each other, and they do. And in solid sodium chloride, that's why they are stuck together as ions, because the positives and negatives attract. Why in the world would they then want to separate from each other just because you put them into water? And the reason for that is that sodium, positive ion, can now have many interactions with the partially negative end of water molecules. They can do this with one molecule here, with another one here, with another one here, with another one, all around it. And this is called a solvent cage. Where the solvent molecules arrange themselves to cage or trap the ion. And in doing so, they satisfy that ion's need to be attracted to a negative charge. In this case, they're attracted to multiple water molecules, so that they're attracted to the negative ends of the water molecules. And the same thing happens with the chloride. Why is it willing to let go of the sodium ion? Because it can satisfy its need to be attracted to positive or partially positive charges by being enveloped in a cage of water molecules where the chloride is then being attracted to the partially positive dipole end of the many water molecules. So this is an ion-dipole interaction, or ion-dipole force. Now, I've included it here, even though it's not technically an intermolecular force. Because remember, intermolecular means between two molecules. This is between one molecule and ions of an ionic compound. So it's not technically between two molecules. But I've included it here, and it is typically included in the list of IMFs because of the similarity of the interactions going on. Now, those are the four types of intermolecular forces that we're going to refer to. And you can see that as we go down this list, these partial positives and partial negatives tend to get larger and larger and larger, and therefore the intermolecular forces tend to get larger and larger, because fundamentally, intermolecular forces are just electrostatic attractions. They're the attractions between positives and negatives. So for London Dispersion Forces, we have small positives and small negatives. So generally we have small attractive forces. As we go to dipole-dipole interactions, dipole-dipole forces are stronger because the partial charges are stronger and longer lived, generally. As we go to hydrogen bonding, typically hydrogen bonding IMFs are stronger still because the dipoles are stronger, and therefore the partial positives and negatives are stronger. All the way down to ion-dipole interactions, which tend to be the strongest yet, because here we're not dealing with a partial positive charge, we're dealing with a full positive charge and a full negative charge on that ion. So just to repeat, these are all electrostatic attractions between neighbors, and therefore the larger the partial or full charge that you have, the stronger the attraction is going to be. Now you may have noticed that I used a little bit of a weasel word by saying generally. The general trend is that I generally increase. So there are some exceptions here, and we're going to talk about that on the next page. But before we go, I just want to note that as we go down this list, we are generally increasing IMF strength. Okay? As we go down that list, generally the strength of those IMFs are increasing. All right, on the next page, I've given you a sample problem, and basically this is asking us to name the strongest IMF in each of the following molecules. So for each of these molecules, I have to determine which IMFs are present And then I have to pick the strongest one. So I'm going to do the first one for us, and then I'm going to let you do the other three as an exercise. So here we have NH3, and I need to determine the strongest IMF in each of these molecules. In order to answer this question, first of all, I have to decide if this is a polar molecule or not. Because if it's nonpolar, then its only IMF will be London Dispersion Forces. If it's a polar molecule, then I have to decide if it meets the special criteria for having a hydrogen bonding situation, or if it's just a regular dipole-dipole force. Well, how do I determine if a molecule is polar? I have to go all the way back and draw the Lewis structure, and then I can base whether it's polar or not on the Lewis structure. So if I draw ammonia, and if I go through the whole process of drawing the Lewis structure, I get this structure. Nitrogen, 3 hydrogens, and a lone pair there. And I ask myself, is this a polar molecule? What 2 criteria have to be met for this to be polar? I have to have a polar bond, at least one polar bond somewhere in the molecule. Do I have that? Yes, I do. That's a polar bond right there. And criterion number 2 is this molecule must be asymmetrical. Is this molecule asymmetrical? Yes, it is. So I have both criteria met. There is at least one polar bond in the molecule, and the molecule is asymmetrical, so it is polar molecule. If it's a polar molecule, then what is its strongest IMF? Well, I know that it has London Dispersion Forces, because every substance has those. If it's a polar molecule, it also has dipole-dipole forces. Is this a special case that qualifies for hydrogen bonding? Well, for that to be true, hydrogen within the molecule would have to be directly bonded to a nitrogen, or an oxygen or a fluorine. And yes, it is. So, hydrogen bonding. So this molecule has London Dispersion Forces, dipole-dipole forces, and we're talking about attractions with its neighbors, dipole forces, and it has the special kind of dipole-dipole force called the hydrogen bond. So those are all of the IMFs in this molecule. Which is the strongest one of these typically? It's the hydrogen bonding, isn't it? So we would say hydrogen bonding force. I could write it out, hydrogen bonding. So it has more than one type of intermolecular force, but this question is saying, name the strongest one in that molecule. So I would like you to do the same thing for the remaining 3. You'll need to draw the Lewis structure, determine if the molecule is polar, and once you've done that, then decide what is its strongest IMF. So go ahead and pause the video now, work on that, and when you're done, you can restart the video, and I'll go ahead and work through the rest of these. Okay, continuing on with this exercise, we're going to go ahead and finish this problem for the rest of these 3 molecules. HBr, if I were to go ahead and write out the Lewis structure, I won't go through all the steps, but it looks like this. Hydrogen bonded to bromine, 3 lone pairs in the bromine. This is a polar molecule because it has a polar bond and it's asymmetrical, so it's polar molecule. So which IMFs does it have? Well, all molecules have London Dispersion Forces. This is a polar molecule, so it has dipole-dipole forces as well. Is it the special case that we call a hydrogen bonding situation? Well, within the molecule, hydrogen is not directly bonded to a nitrogen, oxygen, or fluorine, so it does not have hydrogen bonding. So of the IMFs that this molecule would experience with its neighbor, the dipole-dipole force generally would be expected to be its strongest one. Okay? Continuing on, we've got HCN. And if I were to draw the Lewis structure of this molecule, hydrogen single bonded to a carbon, triple bonded to a nitrogen, and a lone pair on the nitrogen. So I ask myself, is this a polar molecule? Well, it does have a polar bond here. The hydrogen-carbon bond is not polar, but the carbon-nitrogen bond is. So it has at least one polar bond in the molecule, and it is asymmetrical, so it is a polar molecule. So what are its IMFs that it would experience with its neighbor? It would have London Dispersion Forces, because everything encounters those. It's a polar molecule, so it would also have a dipole-dipole force between it and its neighbor. But hydrogen is not directly bonded to a nitrogen, oxygen, or fluorine. Yes, there's a nitrogen, oxygen, or fluorine in the molecule, but the hydrogen is not directly bonded to it. So this is not a hydrogen bonding situation. So here again, the dipole-dipole force would be expected to be the strongest of its IMFs that it would experience with a neighbor. And finally, we have CH4, methane. If I draw the Lewis structure of methane, I get a carbon single bonded to 4 hydrogens around it. And I have to ask myself, is this a polar molecule? This is not a polar molecule. It does not have any polar bonds in here. And the molecule is not asymmetrical, so it fails on both of those criteria. So this is a non-polar molecule. Since it is non-polar, the only interactions that this molecule has with its neighbor are the London Dispersion Force. And therefore, that has to be the strongest of its IMFs, since it's the only IMF. All right, so remember that the key to being able to do this is to determine if the molecule is polar. And to do that, you have to draw the Lewis structure and then ask yourself those 2 criteria questions. 1, is there a polar bond anywhere in the molecule? How do we determine if a bond is polar? Well, the difference in the electronegativities between the bonded atoms is 0.5 or greater up to 1.9, right? That's a polar bond. And then the second criterion question you ask is the molecule asymmetrical or non-symmetrical or unbalanced? And if both of those criteria are met, then it is a polar molecule. If only one or neither of those criteria are met, then it's a nonpolar molecule. If it's nonpolar, then it will only have London dispersion forces. If it's polar, it will have London dispersion forces and dipole-dipole forces, and it may also have hydrogen bonding as a special kind of dipole-dipole force. All right, moving on. So we're just going to reiterate the general trend. IMFs in their increasing order of strength of their attraction generally for similarly sized molecules. There's an interesting phrase, and I'll explain why I'm using that phrase here in a moment. So generally, as we increase the attractions for IMFs, we're going from London Dispersion Force, and that's smaller than dipole-dipole force. So dipole-dipole force is greater than London dispersion. And then hydrogen bonding is greater than dipole-dipole force. And then, as we're going in increasing order, the strongest usually, generally, is ion-dipole forces. So again, that is the general trend as we increase in strength of IMFs. But there's a key exception. And the key exception is London dispersion forces are dependent upon size of the molecule. London dispersion forces, the weakest type generally of IMFs, their strengths are dependent upon the size of the molecule. So if we go back over here and we look at our example, you recall how I described how a London dispersion force is generated because of a temporary small dispersion or shifting of this cloud of electron density? Well, the larger the molecule that you get, the larger the cloud is of electron density around it. And the larger the electron cloud is, then when this temporary dispersion occurs, you can get larger and larger and larger partial negative and partial positives. So if you have a very large molecule, let's say Br2 instead of H2, bromine is a very large atom compared to hydrogen. If I have very large molecules, then the London dispersion forces can become fairly large. And in fact, the London dispersion forces of very large nonpolar molecules can become so large, these partial positives and negatives become so large, that they can become larger than the partial positives and negatives of regular permanent standing dipole molecules. So this is the exception. If I have a large nonpolar molecule, I can have a London dispersion force that is actually even stronger than dipole-dipole interactions and hydrogen bonding. So let's write that here in our notes. London dispersion forces are dependent upon the size of the molecule. And so, as we increase the size of nonpolar molecule, the strength of the London dispersion force increases. And sometimes that London dispersion force can get to be so large that it will become larger than regular dipole-dipole forces and even larger than hydrogen bonding forces. So, for example, if I have an H and an H versus a Br and a Br, the Br2 is going to experience a much stronger London dispersion force attraction with a neighboring Br2 molecule than an H2 molecule would with its neighboring H2 molecules. Okay, that's very important. So I'll give you an example here. NH3, we know that from our work up here that NH3 undergoes hydrogen bonding. Br2 is nonpolar, so it has a London dispersion force. So we might normally expect to say, oh, hydrogen bonding, well, that's a pretty strong intermolecular force. It's probably got a stronger intermolecular force than this London dispersion force. But here's an example where it violates that expectation. In fact, this London dispersion force here is greater than this hydrogen bonding. So I'll put a greater sign there, or a lesser sign there, so that the London dispersion force in this case is greater than that hydrogen bonding. Okay? That's a key exception to this. It allows us generally to predict relative IMFs when we're talking about two nonpolar molecules, because generally the larger of these is going to have the stronger LDF.